A Falcon 9 second stage launched from Kennedy Space Center on January 15, 2025, delivered 2 lunar landers and was never deorbited. For 18 months, it drifted through deep space. It is now confirmed to strike the Moon near Einstein Crater on August 5th at roughly 2.6 kilometers per second. This will be only the second rocket to accidentally hit the lunar surface, and no legal framework exists to address what it leaves behind. On January 15, 2025, at 0611 UTC, a Falcon 9 rocket lifted off from Launch Complex 39A at Kennedy Space Center. The flight represented a routine commercial delivery to deep space. Secure inside the payload fairing were 2 independent private spacecraft, Firefly Aerospace's Blue Ghost lander and iSpace's Resilience lander. After a nominal ascent, the Falcon 9 upper stage completed its burn to place the payloads into translunar injection trajectories. Following separation, both landers successfully deployed and initiated their active cruise phases toward the Moon. With its primary task finished, the spent second stage, now designated as Object 2025-010D in the Public Space Catalog, drifted into a wide, highly elliptical Earth orbit. The hardware was unpowered, carried residual propellant, and was expected to tumble indefinitely in the void. At this moment, it was simply another piece of spent machinery. Left in an elliptical Earth orbit with an orbital period of approximately 26 days, the 4,000-kilogram rocket stage began 18 months of unguided drift. Without onboard propulsion or active attitude control, its trajectory was governed entirely by the cold physics of orbital mechanics. As the booster coasted, its path was constantly modified by a complex gravitational environment. The dominant pull of Earth competed with the gravitational influence of the Moon, the Sun, and even the subtle tug of other planets, slowly shifting and stretching the orbit over hundreds of thousands of kilometers. At the same time, non-gravitational forces acted on the metallic structure. Solar radiation pressure, the physical push of photons streaming from the Sun, exerted a continuous force on the vacant cylinder. Because the unpowered stage was tumbling in the vacuum, this solar pressure applied uneven forces, introducing tiny, chaotic deviations that made precise long-term orbital path predictions difficult to calculate over long timescales. Yet, despite these constant perturbations, the spent Falcon 9 stage remained a solid, trackable body of aluminum-lithium alloy, rather than a piece of space debris that simply disappeared from existence. It continued to move through a predictable region of space. Each successive loop brought the dead booster closer to an intersection with the lunar path, leaving a physical trail of coordinates. The coordinates of this drifting path did not remain hidden within proprietary tracking databases. In September 2025, independent astronomer Bill Gray began reconstructing the trajectory of Object 2025-010D. Utilizing his open-source orbital determination software, Project Pluto, Gray integrated publicly available 2-line element data with raw astrometric measurements. These measurements came from a cooperative network of amateur and professional observatories tracking faint, fast-moving points across the night sky. Rather than relying on a single definitive calculation, the orbit solution was a mathematical fit that tightened over several months. By February 2026, the dataset had grown to include 1,053 independent observations from facilities spanning the United States, Europe, and Asia. This extensive tracking history allowed the software to account for solar radiation pressure and gravitational pulls from the Earth, Moon, and Sun, projecting the booster's path with increasing precision. The calculations ultimately revealed that the chaotic orbital perturbations would resolve into a direct lunar collision on August 5, 2026, near Einstein Crater on the western limb. Roughly a year before the event, Gray published his detailed tracking logs, raw orbital elements, and perturbation code online. This public archive established a completely transparent, verifiable record. By making the methodology inspectable, Gray allowed other orbital analysts and planetary scientists to independently download the coordinates, run the numerical integrations, and confirm the calculations themselves. The forecast did not rely on institutional authority. It was a verifiable solution built from open data. The refined orbital solutions lock the collision down to a highly specific window, August 5, 2026, at approximately 6:35 UTC. The terminal point of this trajectory lies near Einstein Crater, positioned on the western limb of the lunar disk. Because this target region sits on the Moon's near side, the entire event remains geographically visible to instruments on Earth as well as spacecraft in low lunar orbit. The spent booster will strike the surface at approximately 5,400 miles per hour, or 2.4 kilometers per second, translating its remaining mass and orbital energy entirely into a kinetic force upon impact. Establishing these precise physical parameters converted the scenario from an abstract tracking exercise into a concrete event. This narrow margin of spatial and temporal uncertainty allowed planetary scientists and space agencies to transition from passive observation to active operational planning. Rather than monitoring a broad, unpredictable orbital sweep, teams began calculating exact telescope pointing vectors and scheduling high-cadence instrument sequences, ensuring that both ground-based facilities and orbital assets would be oriented toward the correct coordinates at the exact moment of impact. NASA's Lunar Reconnaissance Orbiter will target the impact site to capture high-resolution narrow-angle camera imagery before and after the collision. This baseline comparison allows scientists to detect subtle surface alterations. South Korea's Danuri spacecraft is scheduled to pass within 2 miles of the impact zone just minutes before the strike, providing an active orbital platform to monitor the pre-collision environment. While these orbital assets collect empirical data, researchers rely on computational models to estimate the physical consequences of the impact, establishing a clear line between direct observation and simulation. Modelers at the University of Texas have simulated the physics of a booster weighing 4,000 kilograms, striking the regolith at 2.4 kilometers per second. Their calculations predict the kinetic energy will generate a 2-component debris plume with a central spike of fine dust and vapor reaching altitudes of 75 to 100 kilometers, extending laterally up to 180 kilometers. This energy is expected to excavate a fresh crater measuring 20 to 30 meters across and 3 to 4 meters in depth. This process will expose subsurface materials that have remained undisturbed for millions of years. Comparing these predictive models with the physical measurements gathered by the spacecraft turns the event into a systematic test, verifying if simulated scaling law models match actual, observed hypervelocity impact behavior in a vacuum environment. This collision marks only the second confirmed instance of a discarded rocket stage accidentally striking the Moon. The first occurred in March 2022, when a spent Chinese booster impacted the far side. Under the 1967 Outer Space Treaty, which forms the core of international space law, nations must avoid harmful contamination of celestial bodies. Yet, the treaty does not define what constitutes harmful contamination or establish limits on permanent terrain alteration. The 1972 Liability Convention defines rules for damage, but it requires proof of fault for accidents occurring off-Earth and remains untested for lunar surface impacts where no active installation is hit. While the non-binding Artemis Accords establish political commitments for operational coordination, they lack treaty-level enforcement. Space law scholar Michelle Hanlon notes that as commercial traffic to the Moon expands, this regulatory void grows increasingly problematic. Resolving this gap likely requires concrete international standards, including a mandatory lunar impact registry, standardized end-of-life disposal procedures for launch hardware, and designated protection zones for scientifically valuable lunar sites. As lunar traffic accelerates, the legal vacuum surrounding deep space debris remains unresolved. This silent impact is not a mere anomaly, but a preview of an unregulated frontier. How we govern these permanent lunar alterations will define the future of exploration. Share your thoughts on space governance below.